In this lesson, we're going to talk about the procedure of titration and how that can be useful for us to figure out something unknown about acids and bases. Okay, let's throw back to our last lesson on acid-base neutralization. So acid-base neutralization occurs when I have equal moles of the hydrogen ion and the hydroxide ion reacting in a double replacement swapping partners reaction between an acid and a base. In order to achieve complete neutralization, the mole ratio of the hydrogen ion to the hydroxide ion will always be 1:1, okay? I know that I need one of these hydrogen ions and one of these hydroxide ions to create one of these water molecules, okay? Now, it will always be a 1:1, but it does not necessarily mean the mole ratio of the original acid and base that came into this to donate these ions does not mean that the original mole ratio of the acid and the bases also has to be 1:1. You were like, what is she talking about? Well, let's look at this. Okay, so here is the balanced molecular equation of the neutralization reaction between the strong acid hydrochloric acid and sodium hydroxide to make sodium chloride in water, okay? So complete ionization, I would show all of the ions present in solution, okay? I cross off my spectator ions, and yes, boom, the result of a neutralization reaction is going to be the hydrogen ion, hydroxide ion, creating water. Well, let's look at the ratio of the acid of the hydrochloric acid and the base. That's a 1:1 ratio right there, okay? The ratio of the hydrogen ion when it's all said and done and the hydroxide ion when it's all said and done is also 1:1, okay? But it doesn't always have to be that way. Here I have the neutralization between hydrochloric acid, and this time calcium hydroxide is my base. So after I've ionized it completely and crossed off my spectator ions, I still get my same equation of the formation of water from the respective ions. But if I look back up at my original acid and base, I have a 2:1 ratio of acid to base, okay? Still having that 1:1 ratio of the hydrogen ion and the hydroxide ion. Okay, so what does all that have to do? I thought we were talking about titration today. We are, because turns out neutralization reactions have everything to do with the process of titration. A chemistry lab is like a big party. Some drop acid and others drop the base. Titration. Titration is a method that uses an acid-base neutralization reaction in order to determine an unknown concentration of an acid or a base. In a titration, the unknown acid or base is titrated with an acid or a base with a known concentration. You're saying a lot of words here, and I am. Let's break it down. I got a cool picture here to show you what I'm talking about. In any acid-base titration, I got two things here. One will be the titrant, which will be a base in this case, or it could be an acid, and it is located in a burette, okay? This guy will always have a known concentration, and what that means is I will know its molarity. In this case, my NaOH, my titrant, is going to have a molarity of 1.0, okay? The second guy is my analyte. My analyte will be my acid or base inside of a flask, okay? I will not know his concentration typically, okay? So what does this mean? I've got a titrant and I've got an analyte, and we love this so much. So what you do when you titrate is the titrant, meaning the guy in the burette, okay, is actually added dropwise from the burette until an equivalence point is reached, okay? The equivalence point is where neutralization is complete, which we know neutralization is when equal moles of the hydrogen ion and the hydroxide ion have reacted. Once the equivalence point is reached, you stop the titration, meaning I stop dispensing the titrate, and I can then use that information to calculate the concentration of my unknown substance with stoichiometry. And you're like, what is this graph thing over here? Okay, you guys, this graph is tracking the pH of my titrant in the flask over time as I am adding NaOH titrant volume to it, okay? We're going to talk about what that means here in a second. But the technique of titration looks like this, where I'm going to measure out a certain amount of that unknown acid into a flask. I put it underneath the burette. I'm going to take the initial reading on the burette, and I'm going to drip that titrant down dropwise until I will signal neutralization by a color change with an indicator. And then I can take that final reading of whatever is left in the burette. And the difference between that initial and final reading is going to be the amount that was dispensed to reach neutralization. So now let's go back to this There's this curve, the titration curve. Once I get closer to the equivalence point, y'all, the pH just jumps crazy, sharply and suddenly, and then eventually it stabilizes again. Okay, so since calculations involving titration are based on that exact volume of the titrant that was added in that narrow range where neutralization occurs, it's super important to titrate really, really slowly so you don't overshoot your equivalence point. And you're like, what is she talking about here? So if this is tracking over time how much sodium hydroxide I'm adding, the difference between like 20 and 30 in terms of a pH is a giant jump. So this could be looking at the difference between a drop or two, which is why we need a burette as the equipment for adding something very, very slowly. So we want to make sure that we don't overshoot and go too far and miss our equivalence point, because then our calculations will be wrong. So you're like, well, how do I make sure I don't shoot? How do I know? Who's going to tell me to stop? Well, your indicator will, okay, you guys? Your indicator will change color at that anticipated pH of your equivalence point. So seeing the color change at this pH means you have reached the equivalence point and tells you to stop titrating, okay? So looking at this, if I am titrating a strong acid with a strong base, like I am here, we learned last time the pH when neutralization is complete will be equal to 7. This is also the pH at the equivalence point, okay? So I'm gonna wanna pick an indicator that, I don't know, maybe will turn a color in response to that pH change. Well, here phenolphthalein is a very common indicator when you do a titration of a strong acid with a strong base, because that strong acid is going to be clear in phenolphthalein when the pH is less than 7, but as I add base to it, it is a clear just switch that has turned off, that the second it turns basic, it will give you a bright pink color, okay, you guys? So like, not in a cartoon version, this is what this is going to look like. My burette contains the sodium hydroxide titrant, and the flask contains the hydrochloric acid analyte. I drop a few drops of that phenolphthalein indicator into the flask. Then I dispense the sodium hydroxide slowly. You're going to see flashes of pink appear temporarily, but then they will fade away with swirling as you get closer to the equivalence point. And the equivalence point is reached when you have a permanent, keyword here being light pink color change occur. You do not want that pink to get too dark, because that means you have overshot the equivalence point, but that tells me when neutralization is complete and I can stop titrating. Okay, so do not overshoot the equivalence point. You know you are screwed when the color is this dark. If you get to the point of your titration where your color goes this dark, you have to trash all your data and start over again. So it is a very tedious process of titrating. So you're like, great, okay, so that was the pH is 7 at the equivalence point. This is great news for us. Is it always 7? Not always. It depends on the strengths of the acid and the base coming together in the titration. A strong acid and a strong base, when combined in equal molar amounts, will completely neutralize each other, and therefore the pH of the resulting neutralization will be 7. Okay, we've talked about this last time. This is just because both strong substances dissociate or ionize completely. So in our little example that we've been working with, our titrant, sodium hydroxide, yeah, sodium hydroxide is a strong base, and our analyte is hydrochloric acid. Yeah, hydrochloric acid is a strong acid. So we know that the pH at the equivalence point will be equal to 7, okay? So the rule here is a strong acid and a strong base, both strong people come to the fist fight, they're going to have a tie, so the pH will be neutral or 7 at the equivalence point. Amazing. However, we can have weak acids and weak bases too, and they do not dissociate completely. Ooh, how much dissociation occurs and how much the hydrogen ion or hydroxide ion exists in solution is gonna depend on how weak the acid or base is. As a result, the pH at the equivalence point or at neutralization in titrations that are involving weak guys will not necessarily be 7. We've kind of done some of this concept last time, but now we're going to look at it on how it affects these titration curves. We know if I use a strong base in a weak acid in a neutralization reaction, that strong base is going to win the fist fight, and he's going to make the resulting solution basic. Okay, so when I titrate a strong base in a weak acid, the resulting pH at the equivalence point will be basic, greater than 7. Now here's the cool thing. Titration can go both ways. I can have the base in my burette and my flask containing an acid, or I can have an acid in the burette and my flask containing a base. The shape of your titration curve kind of lets you know what you're looking at here. Okay, so let's kind of look at this one first. You're like, what is happening here? Well, the pH, or the y-axis here, is measuring the pH of the guy in your flask, okay? So whatever the thing in my flask is, whether an acid or a base, will let me know based on the starting pH value. So if I see my titration start up here with a pH greater than 7, that lets me know that my analyte is a base, okay? And that means my titrant must be an acid, which means if my titrant is an acid and I add it, it will slowly become more and more and more and more acidic. I hit that large jump, and then it will finish off being acidic, okay? Now, if I titrate that strong base in my flask with a weak acid, the strong base will make the pH basic at the equivalence point, okay? Which is why here my equivalence point is marked with a pH that is still greater than 7. Okay, so this is me adding a weak acid to a strong base. I can also add a strong base to a weak acid, meaning I know I started with an acid because the pH is less than 7, okay? And then if I add base to it, the pH gets more basic or higher, okay? And if that base was a strong base as my titrant, the pH at the equivalence point will be greater than 7. So these graphs are looking at both strong base and weak acid. They're just looking at which one is the titrant and which one is the analyte being flipped. Regardless, pH is going to be greater than 7 at your equivalence point when you got a strong base plan, okay? Strong base makes it basic. All right, what if I have a strong acid and a weak base? Well, if I have a strong acid's going to make the resulting pH acidic, or it will be less than 7 at my equivalence point. Okay, depending on who's the titrant and who's the analyte, I will have different curves, but I will notice that for both of these curves, the pH is 7 at that equivalence point. To figure out who's the titrant and who's the analyte, look at what pH I'm starting. That lets you know whether your guy in the flask is going to be an acid or a base. Here I've started off acidic here, okay? Which means it's going to be in the flask, the acid is in the flask, and then I'm going to be dispensing a base into it. pH less than 7 means that acid that I started off with was strong, and the base I was adding to it was weak. Over here on this graph here, I've started off basic, which means I'm steadying a base. As I'm adding acid to it, the pH drops. I notice at the equivalence point, the pH is less than 7, which means the acid that I'm dispensing into it is a strong acid to a weak base, okay? Strong acids make the pH at the equivalence point acidic. Amazing. Okay, titration stoichiometry. You're like, you were telling me that we're doing all this dropping things into things, and then we're going to have to do some calculations with that. And you're like, oh, it's stoichiometry, you guys, okay? We're just doing a lab technique to use stoichiometry to calculate the unknown of our analyte. Let's look at what this really is going to look like for us.
Titrations can be used to calculate the concentration of acids. Here's our hydrochloric acid of unknown concentration. Using a pipette, we add a 25 cm³ sample to a conical flask. We then take our alkali, sodium hydroxide, of known concentration and add it to a burette using a funnel. By taking note of the starting and final volume, we can see exactly how much alkali was added to neutralise our sample. Our alkali is now ready to neutralise our acid. But first, we add several drops of indicator, such as phenolphthalein, which will turn pink when the acid has been neutralised. Starting with a rough titration, we add the alkali from the burette until we see a colour change, showing that the acid has been neutralised. We take note of the rough volume for our accurate titration. This time we stop short of neutralisation and then add the alkali drop by drop until it turns pink. This improves the accuracy for the final volume. When we get several similar results within 0.1 cm³, we take a mean volume for our final calculation. Let's say we got 43.5 cm³. So how do we use this result to calculate the concentration of our acid? Well, we know that the exact volume of alkali added was 43.5 cm³, or 0.0435 dm³, and the known concentration was 0.1 moles per decimeter cubed. So we can calculate the number of moles of sodium hydroxide in the solution as 0.00435 moles. Now, according to the chemical equation for the reaction, exactly 1 mole of alkali is needed to neutralise every 1 mole of acid. So there must have also been 0.00435 moles of acid in our 25 cm³ or 0.025 decimeter cubed sample. And now the concentration of the acid is simply the number of moles divided by the volume. This gives a concentration of 0.174 moles per decimeter cubed. So that's how to calculate the concentration of an acid using a titration.
So that's in essence what we're really doing when we're doing the calculations from a titration. We're just doing solution stoichiometry where I'm starting with that volume of the titrant that I needed to be dispensed to reach neutralization. I grab that volume using the molarity, figure out how many moles of that guy I have, and then I apply my mole ratio, and then I can calculate stuff of my analyte following. It's just stoichiometry, you guys. I love that so much. Okay, so if I know the concentration of your titrant, and I record the volume of the titrant that was needed to be dispensed, you can calculate the unknown concentration or even what the volume was of your analyte. All right, here we go. So we're going to go through 3 examples, and these are going to feel pretty tedious, but we are at the end of chemistry, so I'm ready to push you guys. So example number 1 says, an unknown volume of 0.500 molar sulfuric acid is titrated with 0.750 molar potassium hydroxide. 10 milliliters of potassium hydroxide were needed to be dispensed to reach the equivalence point. What volume of the sulfuric acid was present in the flask? A lot of times on these titrations, I like to visualize or maybe even draw off to the side who is who having here. Well, my titrant is potassium hydroxide because that says I'm dispensing it into the flask to reach neutralization at the equivalence point. Okay, the sulfuric acid is inside of the flask because they even told me that stuff right there. Okay, so if we are doing some calculations with this chemical reaction between this acid and this base, this is some stoichiometry, which means we need a balanced chemical equation. So maybe let's write that. So my reactants are going to be sulfuric acid and potassium hydroxide. Okay, double replacement neutralization reactions are swapping places. So my products are always going to be salt and water. So my salt is going to be potassium sulfate and HOH is my water. So then balancing it, I've got everybody balanced to satisfy the law of conservation of mass. So this is the reaction equation I'm dealing with. I know who my titrant is. I know who my analyte is. Now I'm ready to dissect this problem and read what the words are telling me. Okay, what are they asking me to solve for? What volume of sulfuric acid is present in the flask? Typically with titration, as you can see with those very small graduations in a burette, we're talking about milliliters. Small amounts is what we typically solve for a volume. So we're solving for the milliliters of sulfuric acid. If you'll notice, I underlined the molarity of that sulfuric acid because that will allow for me to use it as a conversion factor to convert from a volume to moles, okay? Then where am I starting from? Well, how much volume did you dispense of your titrant, okay? They told me that 10.0 milliliters of potassium hydroxide was needed to reach the equivalence point, okay? Well, what's the molarity of that potassium hydroxide? It's right here, 0.750 molar, okay? So my starting amount is the starting volume of the dispensed titrant, and my ending is, well, how much volume was in this analyte of the sulfuric acid? Okay, so we get ready for some stoichiometry. I'm going to first make that volume of potassium hydroxide liters, right? Okay, so to make it liters, you bump the decimal place back 3 times or you divide it by 1,000. So I actually have 0.10 liters of potassium hydroxide. And then I grab that molarity. That molarity means that there are 0.750 moles per liter. So that means I can make this statement, oh my gosh, there are 0.75 moles per 1 liter as a conversion factor, which will then allow me to cancel off liters on top and on bottom of potassium hydroxide. I've now made it to moles, which means I take the coefficients between the potassium hydroxide and the sulfuric acid and use them as a mole ratio, stating that there are 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. Okay, that cancels off the moles of potassium hydroxide. I'm now at moles of sulfuric acid. I've forgotten where I am taking it to. No, you did not, because we wrote it underneath our problem and it's very helpful. Well, how do I take this to a volume, like a milliliters? Well, I gave you the molarity of the sulfuric acid. Remember, that's however many moles you have in a liter, okay? I can use that as a conversion factor down here and say that, well, oh, that means there are 0.5 moles of sulfuric acid in 1 liter of sulfuric acid. Okay, so the moles of sulfuric acid cancel each other out. I've solved for liters of sulfuric acid, okay? But the answer most appropriately will be written in milliliters because we're dealing with small volumes. So to turn that liters to milliliters, I move the decimal place back 3 times. So I have 7.50 milliliters of sulfuric acid. Noticing I'm keeping consistent with my sig figs, you guys, okay? The sig figs in my problem were all 3 sig figs, so that limits me to having also 3 sig figs in my final answer. Okay, so y'all, it's just stoichiometry. We did this last unit, except now we are doing it applied to the lab technique of titration, which is really fun and really cool. Let's now think about what this means in terms of this process of doing this, in terms of, like, I don't know, some titration curves. Okay, so here would be kind of a titration curve of this titration that the problem is describing. You're like, what is she even going on with this? Well, it all depends on who is the who, okay? We said my analyte, or the guy here in the flask, was sulfuric acid, okay? Well, we measure the pH of the guy in the flask throughout a titration curve, okay? We know that the x-axis for these titration curves are the volume of the base that is being dispensed, or the substance, the titrate that's being dispensed. So I can label my axes here depending on what this specific titration is, where this would be my titrant, the KOH, and this pH of my analyte would be the sulfuric acid. Okay, remember the pH is always starting of what my identity of my analyte is, so it is no wonder that my starting pH is acidic because I got an acid in there, you guys, okay? As I add base to it, yeah, the pH rises to get more basic, okay? So the key thing here is I know I have an acid in there, so it must start acidic. And I know I'm titrating it with a base that will eventually end up basic as I've reached neutralization and pass if I keep adding more base, okay? The next thing I can kind of identify here is, y'all, ooh, notice what volume that equivalence point is hit by. I told you in the problem, it took 10 milliliters of that base that was needed to reach the equivalence point. Well, boom, my equivalence point better be where that volume was represented for reaching that neutralization. So here is 10 milliliters of the potassium hydroxide at the equivalence point, okay? The next thing I can look at is I could be able to predict where on the y-axis the equivalence point will hold. It all depends on my strengths of my acids and my bases, okay? Both potassium hydroxide and sulfuric acid are strong. So a strong guy and another strong guy is going to be a tie in the fist fight, which means my pH will be 7 at the equivalence point. Lots of good stuff to get from this. We can be able to predict whether it slopity slopes up or slopity slopes down, depending on if I'm titrating an acid with a base or a base with an acid in this case, or if I'm titrating an acid with a base or a base with an acid. In this case, this is titrating an acid with a base, okay? I can also identify where on the x-axis that volume is at the equivalence point, and I can identify where on the y-axis that pH is according to the strengths. Lots of talking. Let's do the next example. Okay. In a titration, 15.7 milliliters of 0.250 molar hydroiodic acid completely neutralizes 20 milliliters of ammonium hydroxide. What was the molarity of the ammonium hydroxide? You're like, okay, y'all, we're doing a titration. Let's visualize what's happening here. So I've got hydroiodic, and it completely neutralizes ammonium hydroxide, which means I'm titrating a hydroiodic acid is the titrant, and the ammonium hydroxide is my analyte at the bottom. Okay, I've got the visual. Okay, I also have the visual of who my reactants are. I better write a reaction equation so I can do the stoichiometry that's required for this problem, which means my reactants are the ammonium hydroxide and the hydroiodic acid. They swap partners to create neutral water and a salt. Okay, they create the salt of ammonium iodide, and my HOH is water. It looks like we are already balanced, so now we're ready to read the problem and be like, okay, well, what are they asking me to solve for? No, they're asking me to solve for the molarity. You're like, that's not a volume or moles or grams. It's not. Molarity is moles divided by liters. Y'all, if you get to a problem like this when they're saying, well, what is the concentration? I got to solve for the moles of ammonium hydroxide first. And then maybe I can do something cute like pair that with the volume of ammonium hydroxide and then maybe calculate the molarity. But yes, if you see solve for the concentration or the molarity, you solve for moles first and then you pull that out of stoichiometry and proceed like normal. Okay, well, the given amount of information is the fact that they told me that I needed 15.7 milliliters of 0.25 molar hydroiodic acid. Okay, my given is going to be the volume of that titrant that you've dispensed. So me kind of creating this picture helps me out a little bit better with figuring out where it is I am starting from on my stoichiometry with all of these numbers involved sometimes, because I know I'm always going to be starting with that volume of that titrant. Okay, amazing. So first thing I got to do is I'm like, boom, well, first of all, make that milliliters liters. So I have 0.0157 liters of hydroiodic acid. Okay, well, to convert this to moles, do I have the molarity of the hydroiodic acid? I sure hope I do. I sure hope my titrant has a known concentration. It does. It is 0.250 molar, which means there are 0.250 moles of hydroiodic acid in every 1 liter of it. So liters of hydroiodic acid go away. I'm at moles of my given mole ratio time between my hydroiodic acid and my ammonium hydroxide. That is a 1-to-1 ratio, meaning they're ones as those coefficients, which means moles of hydroiodic acid are canceled out. So now, according to this, I'm going to stop here because the whole purpose of my stoichiometry was to solve for moles of ammonium hydroxide. And that is the only unit I do not have, or I have not canceled off. So that will be the unit that I'm solving for here. So when I do the steps, I get 0.00393 moles of ammonium hydroxide. You're like, that is a very small number. Well, yes, guys, I'm dealing with very small amounts. So it's very, it's not unusual for the amount of moles of things that I'm actually looking at to be very small. So do not stress about that. Noticing I'm retaining the 3 sig figs that I'm seeing in all of the other values that I've provided you with. So I've solved for moles. You're like, what do I do? They're asking me, they wanted me to solve for the molarity. Well, yes, molarity, you guys, is moles divided by liters. Yeah, I just solved for the top number. Well, where am I going to get the bottom number? Where am I going to get the liters of the ammonium hydroxide to find the molarity of the ammonium hydroxide? Isn't the problem? I told you that it neutralized 20 milliliters of ammonium hydroxide. Oh, I got everything I need. I take the moles, put it there. I take the volume, except I'm converting it to liters, right? And then I divide and I get my molarity. Congratulations, you have discovered or figured out through calculations from a titration what the concentration was of this unknown sample of ammonium hydroxide. So now let's look at what a titration curve may look like for a titration such as this, okay? So what I would want you to look at is based on what you're visualizing, meaning who is the titrant and who is the analyte. You would know whether it's going to slopity slope down or slopity slope up, okay? The pH of my analyte is what is measured, meaning I'm measuring the pH of the sodium or ammonium hydroxide throughout the course of titration, okay? Which means if it is a base, that is going to start off basic at the start of titration. I am adding an acid, which means my x-axis is going to be the volume of the acid or the hydroiodic acid that I am adding. So I'm starting basis because I have a base in here. I add acid, so it's going to end acidic, okay? And then I know where my equivalence point will be. On the x-axis, it's going to be at the volume of that titrant that was needed to be dispensed to reach the equivalence point. And the problem they told me it was 15.7 milliliters. That was the value, the number I started stoichiometry with, right? It always will be, okay? We know the equivalence point would be hit at that volume. As to at what pH the equivalence point would be hit by, that's where I'm looking at the strengths of my acids and bases. Ammonium hydroxide, he's weak, but hydroiodic acid is a strong acid. So I'm noticing that the pH at the equivalence point will be acidic or less than 7. So I'm able to predict that it will start off basic and end acidic depending on who is the acid and base in my titration setup, right? And then I'm able to predict what the pH is at the equivalence point and at what volume the titrant was added as well. Okay, last example. It says 45 milliliters of acetic acid in a flask was titrated with 1.50 molar calcium hydroxide. 34.7 milliliters of calcium hydroxide were needed to be dispensed to get to the equivalence point. what was the concentration of the acetic acid? You're like, okay, who is who in this game of playing titration? Okay, you guys, y'all, we've got acetic acid in the flask. They told us it was in the flask, okay? They also said we added a certain volume of calcium hydroxide, or we've dispensed the calcium hydroxide. So that means my titrant in the burette is going to be the calcium hydroxide. Great. These are my reactants for my equation. Acetic acid plus calcium hydroxide, double replacement neutralization reaction to create salt in water. The salt that is created is going to be calcium acetate. Man, we love that acetate polyatomic ion. There's a lot going on there. Okay, once again, HOH is my water. To balance, I provide the coefficients that you see, and now we're ready to read the problem. You're like, okay, well, what is it that they are solving? What are we solving for? Concentration. Concentration, the concentration of something is molarity. Molarity means that we're going to take moles over liters, which means we need to figure out moles first, which means we're taking our stoichiometry to moles. We are solving for the moles of acetic acid. Okay, well, where are we starting from? We're going to start from the volume of the titrant that was needed to be dispensed, meaning the 34.7 milliliters of that titrant calcium hydroxide, knowing that it has a certain concentration, which we're going to use as a conversion factor in our stoichiometry. Okay, so we're going to set it up. That is our volume, 0.0347, but liters. That will then allow us to take 1.50 molarity and say that there is 1.50 moles of calcium hydroxide in every 1 liter. So this is molarity as a conversion factor, which will allow for us to convert from my volume or my liters to moles of my known, or my given value, my titrant. Okay. Now I'm at moles of my given, so I'm ready for the mole ratio, which means I grab the coefficients between my given substance and my unknown. It looks like it is a 1:2 mole ratio between calcium hydroxide and acetic acid, and that will allow for me to now get to moles of my acetic acid. And this is where I'm going to stop, because we're going to use this to solve for the moles of acetic acid, which means we get 0.104 moles of acetic acid. Well, the point of doing this is now we have our mole value to solve for molarity. So this mole value goes on top. I go sneak up in the problem and grab whatever the original volume was of this analyte, acetic acid, and I pop it down here on the bottom just in liters, okay? So dividing those values, I get a molarity of 2.31 molar acetic acid. So that was the concentration of the acetic acid that I did not know until I did the wonderful process of titration. Noticing that I'm keeping sig figs. 3 sig figs are in my answer because all of the values in the problem also have 3 sig figs. So what would a titration curve for this titration look like? Okay, so it all depends on if you're slopity slope up or slopity slope down. Well, what is your analyte? Well, it was an acid, so I better see it start down here on the bottom, meaning an acidic pH, because this is what I'm measuring, the pH of that analyte right here, okay? So that means it'll start acidic and it will finish off basic, so it will slope up, okay? Where that equivalence point is will be at a certain volume. Well, first of all, it starts off acidic and it ends basic. And the volume of the equivalence point will be the amount of the calcium hydroxide titrant that needed to be dispensed to get to that equivalence point. Once again, that's the value that started our stoichiometry. That was the magic number that allows us to do all of these wonderful calculations. And then to figure out what the pH at the equivalence point is, well, I gotta look at the strength. I have a strong base in calcium hydroxide, and I have a weak acid in acetic acid. So that means my strong base in a fight with a weak acid is going to be basic at the end, which means my pH at the equivalence point will be basic or greater than 7. So that is what acid-base titration is. It is, guys, we've done it. We've come this far with our stoichiometry journey here, and we're now applying it to this amazing lab technique of titration, which lets us use acid and base neutralization to discover an unknown concentration of a solution in chemistry.